Welcome, curious minds, to another deep dive.
Great to be here.
Today, we're tackling a headline that honestly sounds like something straight out of, well, an old storybook.
Uh-huh.
World's largest collider finds modern alchemy as U.S. tech turns lead to gold.
Yeah, lead into gold, it definitely grabs your attention.
It really does.
Yep.
So we're talking about actual gold nuclei being detected, made from lead, not magic, not philosophy, but particle physics at the Large Hadron Collider.
Exactly. At the LHC on the French-Swiss border, it's quite something.
So our mission in this deep dive is basically to unpack this. We want to get into the science, especially these ultra-peripheral collisions they talk about.
They're key.
And also, the technology and the people who actually managed to spot this. We want to give you the core facts, the aha moments, without drowning you in jargon.
Making sense of the science.
Exactly. And hey, if you find this stuff as fascinating as we do, please do like this deep dive, subscribe for more, maybe check out the affiliate links if you're curious, and definitely tell us in the comments what else you'd like us to explore.
Yeah, let us know.
Okay, let's dive in. Lead into gold. I mean, my first thought, honestly, ancient alchemists, right?
Oh, absolutely. The Philosopher's Stone, the whole quest.
Yeah, centuries of people trying to do exactly this. It was the ultimate impossible dream. So seeing it happen now, even on this tiny scale, in this, super high-tech lab.
It is astonishing. It feels like science finally achieving something that was pure fantasy for ages.
Doesn't it? So what's the actual core finding here? What did they really see?
Okay, so the core finding is very specific. Researchers at the LHC detected the nuclei of gold atoms.
Nuclei. Okay, not like solid gold bars appearing.
Definitely not gold bars, no. We're talking about the heart of the atom. And crucially, this didn't happen from just smashing lead ions together head-on, which is what you might typically think of.
Right, the usual collider smash-up.
Right. Exactly. This came from something different, these unique near-miss interactions. And that's what really pushes the boundaries. It challenges how we thought these interactions always worked.
Near misses. That sounds less dramatic than a full collision.
In a way, yes, but the physics is incredibly powerful. It's part of something called ultra-peripheral collisions, or UPCs.
UPCs, okay.
And the source material mentions this discovery sparked both fury and hope.
Fury and hope. That sounds intense. Why fury?
Well, the source doesn't deeply elaborate on the fury, maybe hinting at the implications of manipulating matter. But the hope is clear. It's the excitement of discovery pushing boundaries. It sort of touches on these deep-seated human ambition, maybe even fears, about controlling nature's building blocks.
Huh. That makes sense. It does make you ask straight away, how on earth is that even possible? And then, what does it actually mean for how we understand matter?
Precisely the questions we need to dig into.
Okay, let's do that. These near misses, these UPCs, if the particles don't physically touch, how does that work? How does energy get transferred to, knock bits off a lead nucleus and turn it into gold? It feels counterintuitive.
It does seem that way at first, yeah. But it's all about the incredibly powerful fields involved. So UPCs, ultra-peripheral collisions, think of it like two giant super fast trucks driving past each other on a highway, really, really close, but not actually scraping paint.
Okay, got the image. No direct impact.
Right. No direct impact of the nuclei themselves. What happens is the particles they use are heavy ions, basically lead atoms stripped of their electrons, so you just have the dense, positively charged nucleus left.
Lots of protons packed in there.
Exactly. Lead has 82 protons, and when you accelerate something with that much positive charge to nearly the speed of light, like they do at the LHC, it generates an absolutely enormous electromagnetic field around it, incredibly intense.
Ah, the field. Okay.
Yes. And as these ions zoom along, that intense, rapidly changing field causes them to emit very energetic photons, packets of light, essentially, but way more powerful than visible light.
High energy photons.
Extremely high energy. Now, here's the clever bit. In that near miss, a photon emitted by one speeding ion can fly over and slam directly into the nucleus of the other ion passing by.
So it's a photon hitting the nucleus, not nucleus on nucleus.
Precisely. That's the core of a UPC interaction in this context. It's often called a photon collision or photon nucleus interaction. And the beauty of this, why physicists get excited, is that it's a much cleaner interaction.
Cleaner? What do you mean?
Well, in a normal head-on collision, everything shatters. You get this huge, messy spray of hundreds, thousands of particles flying everywhere. It's really hard to pick apart exactly what happened.
Like a fragmentation grenade going off.
Kind of, yeah. But with a UPC, because it's just this photon interacting, you don't get all that debris. It's a more focused, high-energy glimpse into the nucleus without the shrapnel.
Okay, that makes sense. Cleaner data.
Much cleaner. And because that incoming photon carries so much energy, when it hits the lead nucleus, it can actually knock protons right out.
Just eject them.
Yep. The energy is enough to overcome the forces holding the nucleus together and kick a proton, or maybe several, clear out.
And changing the number of protons.
Changes the element, exactly.
Yeah.
Remember, lead has 82 protons. Gold has 79.
So if you knock out 3 protons...
Bingo! You've transformed a lead nucleus into a gold nucleus. The energy from that photon interaction causes the transmutation. They also saw other transformations, like lead turning into thallium or mercury, depending on how many protons got ejected.
Wow. So it really is like a focused beam of light fundamentally changing matter. That's
wild.
It is pretty wild. It's quantum electrodynamics playing out on a nuclear scale.
But hang on, if these interactions are so clean and maybe less dramatic than the big crashes, how did anyone even notice them? Spotting a single photon knocking a proton out must be like finding a needle in a cosmic haystack. That's an excellent point. It is incredibly difficult, like trying to hear a tiny pin drop during a rock concert.
So who are the eagle eyes here? How did they manage to see this?
Yeah, this is where the human ingenuity and specific technology comes in. Our sources point to Daniel Tapia Takaki and his team at the University of Kansas. They're part of the ALICE experiment at the LHC.
ALICE, okay. One of the big detector experiments there.
Correct. And this team, the KU team, has really specialized in looking for these subtle, clean, photon-type interactions.
Why is it so challenging? You said they're cleaner.
They are cleaner, but they're also much rarer than the big, messy collisions. And the signals they produce can be faint or easily lost in the background noise of everything else happening in the detector. The source material mentions these interactions often go unnoticed by the wider community because they're just harder to isolate.
So you need special tools, special techniques.
Exactly. The KU team developed innovative detection techniques, new algorithms, new ways of sifting through the torrent of data from ALICE, specifically designed to pull out the signatures of these UPC events.
Ah, so it's about the software and the analysis as much as the detector hardware.
Very much so. Advanced analysis is crucial. Their technology, their methods, played a crucial role, according to the sources, in actually capturing evidence of these fleeting particles changing lead into gold nuclei.
It's impressive.
It really is. And it gets even more interesting. Some of these precise, high-energy photon interactions, even though they're clean, can dump enough energy in one spot to actually trigger safety alarms within the collider.
Seriously. So they're subtle but powerful.
Exactly. It gives you a sense of the energy involved and just how sensitive the detection needs to be. So developing these techniques isn't just for cool science discoveries. It's also vital for understanding everything that's happening inside the collider, for safety, for efficiency.
It really highlights that breakthroughs need both the big machines and the clever ways to actually see what the machines are showing us.
Absolutely. New tools often lead to new discoveries, seeing the previously invisible.
Okay, so we have lead nuclei becoming gold nuclei via these near-miss photon interactions, spotted thanks to clever detection techniques. But let's be realistic. You said no gold bars.
Right. The amount produced is infinitesimally small. Like individual nuclei. We're talking fundamental physics research, not industrial production.
Okay, good, because my next question was going to be about the gold price.
No, the gold market is safe.
So what is the bigger picture then? If it's not about making gold, why is this finding important? Is it just a neat trick, or does it point towards something more profound?
Oh, it's definitely more than a neat trick. It's profound in terms of fundamental understanding and future research. Think about future colliders.
Bigger ones?
Much bigger. There are plans, or at least proposals, for colliders that could be, massive. Up to 60 miles long, some concepts suggest.
60 miles? Wow.
Yeah, and when you're designing and running machines on that scale, you absolutely need to understand all the types of interactions that can happen, including these UPCs. Understanding the byproducts and nature of collisions, as the source puts it, is critical.
So studying these cleaner UPCs now helps plan for the future.
Precisely. Because UPCs offer this valuable perspective, giving insights without the complexity of particle sprays. It lets scientists test theories about the electromagnetic force and nuclear structure with greater clarity.
A cleaner window into the subatomic world.
You got it. The work being done now at the LHC, like the stuff from the KU team, is building the foundation, the techniques, the understanding that will be absolutely essential for experiments at those future, much larger colliders. Precise detection will be key.
So for you listening, why should you care about a few gold nuclei? What's the takeaway?
Well, the takeaway isn't the gold itself, it's about the capability. These new methods, this ability to see and analyze interactions we couldn't easily study before, that's the real breakthrough.
It's about refining our tools.
Exactly. Refining our atomic toolkit. It's about getting better at observing and maybe eventually manipulating matter at its most fundamental level. And that could have long-term implications we can't even predict yet. Maybe new materials, maybe better understanding of processes in stars.
Like neutron stars, maybe? Don't crazy things happen in there?
Absolutely. The conditions inside neutron stars involve immense pressures and energies where elements are transformed. Studying these processes in the lab, even via UPCs, can give us clues about those extreme astrophysical environments. It pushes the boundaries of our knowledge about the universe.
So it connects the incredibly small to the incredibly large.
That's often how fundamental physics works, yes.
Amazing. Okay, that brings us towards the end of this deep dive. It's been pretty mind-bending, I have to say.
It's fascinating stuff.
Let's just quickly recap the main points for everyone.
Sounds good.
First off, modern alchemy is, in a very specific sense, real. Lead nuclei were transformed into gold nuclei at the LHC. It actually happened.
Check. Point one.
Second, it happened via these unique ultra-peripheral collisions, not direct smashes, but near misses, where powerful fields create energetic photons that do the work of changing the element.
Right. The photon-nucleus interaction.
Third, spotting this wasn't easy. It took brilliant people, like the team from the University of Kansas, developing really innovative detection techniques to actually see these subtle, clean events. Human ingenuity was key.
Absolutely crucial. The technology and the analysis.
And finally, this isn't just some weird one-off discovery. It's a stepping stone. Understanding UPCs is vital for future, even bigger colliders, and for gaining deeper insights into how matter itself is put together.
Yeah, it's foundational work for future physics. Which leads to that provocative thought, right?
Yeah.
The question posed in the source.
Right. As scientists get better and better at studying these UPCs, these sort of delicate interactions,
Yeah.
what else might they find?
What new fundamental insights are waiting? What other transformations might be possible?
Exactly. What happens when we get even better at seeing these things? Could we discover new particles, new phenomena, maybe even eventually create elements or states of matter we haven't seen before?
It really opens up possibilities, doesn't it? The universe still holds secrets.
It certainly seems that way. Well, thank you for joining us on this deep dive into a truly extraordinary bit of science.
My pleasure.
We hope you're walking away with a clearer picture of this modern alchemy. Keep asking questions, keep exploring, and please do like, subscribe, check out those links, and let us know what you want us to dive into next time.
Thanks, everyone.
Until next time.